Good morning, dear students, and welcome to Vista's e-learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we discuss an important law that was given by Sir Isaac Newton. So this is Newton's laws of motion, part 2, session 2 of the chapter Laws of Motion. So until this point, we have learned Newton's first law of motion, where it stated any object continues to be in a state of rest or in a uniform motion along a straight path until it is made to change its state by an external force that is acting on it. So now that we have understood the first law, we move on to the second law, to understand what is this external force. So to understand the concept of an external force, we begin with momentum. And we define momentum as a product of mass and velocity. Let's take the case of a ball. This ball currently, which is at rest, drops to the ground. Wonderful. So what happened to its momentum? Since initially it was at rest, the velocity is 0. So its initial momentum is 0. And as it falls to the ground, its final momentum will not be equals to 0 because it falls at a certain velocity. Let's consider the mass of the ball is about 100 grams. Initial velocity of the ball is 0 and the final velocity of the ball is 30 meters per second. So can we determine how much will be the change in momentum? Certainly. Why not? Change in momentum is defined as final momentum minus the initial momentum. What is the final momentum? Since we know we define momentum as product of mass and velocity, so final momentum will be mass times the velocity. Final momentum PF, which is equals to, since it's 100 grams, which is equals to 0.1 kg. So 0.1 times 30, and 0.1 times 30 is 3 kg meter per second. That would be the final momentum, and the initial momentum, which is 0.1 times 0 kg meter per second. Final momentum minus the initial momentum give you 3 minus 0, which is equals to 3 kg meter per second. So this will be the change in momentum. So not that hard to identify the change in momentum, isn't it? But what does Newton's second law state? Here's the statement for Newton's second law. Oh, the statement is not yet here. So let me state Newton's second law. We will also look at the statement in the next case, but Newton's second law states that the force acting on an object is equals to the rate of change in momentum. We've already learned change in momentum. So what does it mean, rate of change in momentum? Let's take this example of kicking of a football. When this football is kicked, the ball displaces. Quite simple action. Kicking a football, you kick a football and the ball displaces. Oi, here we go. Like I told you that I will show you the definition later stage. The rate of change of momentum of a given object is proportional to the applied force in the direction of force. rate of change of momentum. We have observed only this part, the change of momentum, but what about rate of change? Now, when you use the word rate of change, it means with respect to time. For a given period of time, how much does a momentum change? That is called rate of change, which is proportional to the applied force, like this kicking of a football. So let's look into the various factors. Ball initially at rest, its initial velocity, so let's call it u. Once the ball displaces, its final velocity is v. Mass of the ball is m. The time taken for it to change from u to v, okay? The time taken for it to change from u, which is the initial velocity, to v, to a final velocity, is t. So, the mathematical formulation of second law of motion. So how do we put it in a mathematical format? Now that we have just understood by a statement the rate of change of momentum with respect to time, let us try to see the mathematical formation. First, we have force that is directly proportional to change in momentum over time. Rate of change in momentum, that is with respect to time. So now we write F that is directly proportional to delta P and delta T. Delta T represents the time. All right, good. So now F is proportional to delta P. Momentum is defined as a product of mass and velocity. Mass and velocity by delta T. Wonderful. Now we have m and v. M is a scalar quantity, v is a vector quantity. So this delta is applicable for v. Okay. Yeah. So here I write F, which is directly proportional to m delta v by delta t. Rate of change in velocity. Where have you understood this? In the previous chapter, motion in a plane or motion in a straight line, there we have learned the rate of change in velocity or the change in velocity with respect to time is called acceleration. Yes? So F, that is directly proportional to m times a, where a is called acceleration. So for those of you who have missed the concepts based on the rate of change in velocity or the rate in change in position, which is explained in the first and the second chapter, you can log in www.v-learning.in. There, under the playlist, you see the previous sessions where the explanation for the rate of change of velocity giving a new physical quantity, which is acceleration. And so is the case for a rate of change in position and many more. So go ahead and try to look at them, have a view. So, yeah. Right. So now we have force that is directly proportional to mass times acceleration. This seems to be very familiar to you because you have learned this in the high school, right? So F directly proportional to m times a. So we have to introduce what is called as a proportionality constant where F is equals to kma. Fk is called the proportionality constant. K is proportionality constant. Right. So how much is the value of K? If 1 unit of force is defined as the amount that produces an acceleration of 1 meter per second in an object of 1 kg of mass. So if you have 1 kg of mass and you apply 1 Newton of force, then you have acceleration of 1 meter per second that is observed. So what happens to the value of K? K in this case becomes 1. Since the K value is 1, your final expression becomes F equals to M times C. Not bad. This is pretty easy. There's also another way to express this following equation, which is for, sorry, not the expression for force. Okay. There's also another way. Okay, so let me mention it here. The other method to express this force is change in position. So change in momentum, delta P by delta T. By applying limits, you get F equals to dP by dt. So this is another expression with the help of a differential calculus. Force is given as a differential form of delta P by delta T. So momentum can be along x-axis, y-axis as well as z-axis respectively. So net force on an object, net force F, which is equals to momentum that is along the x-axis plus momentum that is along the y-axis. Sorry, not just the momentum, the rate of change in momentum along the x-axis, rate of change of momentum along the y-axis, and the rate of change of momentum along the z-axis for a 3-dimension. So this is how you obtain the net force F, which is equals to dpx by dt, dpy by dt, and dpz by dt. Okay, so I have a practical problem that is based on this, where certain numbers are given. You have to identify what is the force. So go ahead, make a note of these numbers. Initial velocity is 0, final velocity is 40, time taken is 4, mass is 100 grams. How much will be the force applied on that ball? Pretty straightforward. Now let us move into examples of Newton's second law where we can observe catching of a ball. So when you have to catch a ball, you lower your hand a little as you catch the ball, you lower your hand a little and then catch it. Why do you lower your hand? What happens if you don't lower your hand? Now, if you don't lower your hand, then the ball's full force is then absorbed onto the hand, which means you get pain. So you'll experience more pain when you catch the ball without lowering your hand. But as you lower the hand, what happens is you are increasing the time of catch. When you increase the time of catch, you are reducing the force. How do we know this? Let's take a look at it. Where F is equals to dP by dt. By increasing the time of catch, so the denominator increases. If the denominator increases, then what happens to the result? Decreases. And that is how you can reduce the force of impact on your hand. All right, so you have to lower your hand when you catch a cricket ball. Let's take a look at an example, another picture or a video of a catch. You see, he drops the catch. Now, why does he drop the catch? Look at that. He drops the catch because he did not lower it enough. So when you lower it enough, you reduce the force and it is easy to catch the ball. If you do not lower it, then you get hurt, plus you drop the ball. So it's a human instinct. When you feel pain, you let go of it. So especially when you touch hot objects, you experience pain. So what do? Do you still hold on to those hot objects? No, you let it go. Similarly here, he experiences pain and lets go. Now, let's look at a friend here. So when he catches, yeah, that's the best. That's the best thing you can do. Instead of catching the ball, just wait for the ball to hit the ground and then you can collect it. One more time. He waits for it, hits the ground. Like, good. So that's a better option. Let the ground take the hit for you. All right, so I hope I've made this concept clear about Newton's second law. So in the next session, we will start with Newton's third law. We will discuss more examples based on this third law. So until then, these are Newton's third law. Until then, I wish you a good day and take care. Bye-bye.